Okay, in this lecture, we're going to talk about Newton's laws of motion. So this is going to cover chapters 5, some of 6, and a little bit of 7. Isaac Newton was born in 1642 and he died in 1727. He was an English physicist and mathematician, and by the age of 31, he discovered the laws of motion, universal gravitation, and calculus. He was quite eccentric, and if you want to know more about him, you can read the book called The Coming of Age in the Milky Way by Timothy Ferris. And it's written for the layman, so you don't have to know a lot about physics or the scientists at the time. I've heard it's really an interesting read and a fun read, not too heavy. Okay, so we're going to talk about forces. So how do we start off? Well, a force is a push or a pull. An object at rest needs a force to get it moving, and a moving object needs a force to change its velocity. Forces arise from interactions, which we'll talk about in a minute, and we can measure the magnitude of a force by using a spring scale. So in this example, we have a box of olive oil, and if we want to be able to pull it to get it moving, we can measure the force that it takes to get it moving using that spring scale, and that'll tell us how many newtons it takes to move that box. So how do we identify forces? Usually there's 2 steps. One is we create like a boundary around the object of interest, and then we say, what is the object touching? So what's in contact with the object? And the other one is, what is the object interacting with long range? And so in this semester, we'll only be talking about gravity, but we'll talk about the long range forces of electric forces and magnetic forces next semester. So all forces fit into these 2 categories, right? When we put a boundary around our object, we can talk about contact forces, so what's touching the object, and long range interaction forces. And so what is the object interacting with long range? And like I said, we'll be only talking about forces or gravitational forces in this semester, and we'll talk about electromagnetic forces next semester. So for contact forces, the 3 we consider are spring force, compression force, and tension force. And so just to further talk about the contact interaction, because we can easily figure out the long range interaction. This semester we just know it's gravity, but for the contact interaction we have to decide what kind of force we're talking about. So if we want to talk about a compression force, we can talk about the contact between 2 solids. So in a minute we'll talk about a book on a table, and so what's in contact with the book, the table is. So and both of those are solids. And so we can talk about the normal force, and the normal force acts perpendicular to the surface, and a frictional force, and the frictional force acts parallel to the surface. And that's for, remember, that's for 2 solids. And when we want to talk about friction, we'll talk about static friction. And when we have static friction, the object isn't moving. And when we talk about kinetic friction, our object is moving. When we talk about the contact between a solid and a liquid, we'll talk about the drag force, right? And we might talk about the drag force if we're talking about a rocket and the velocity or the drag that acts on the rocket as it flies into the air, right? There's a drag force. We can talk about a thrust force. So if a rocket has an engine that's firing, that fuel that's on fire creates a thrust upward for the rocket. We can talk about the buoyant force of water on, say, the hull of a ship. And we can talk about the lift force maybe for an airplane, where the air underneath the wings creates lift to cause the airplane to fly. So if we want to think about step 1 in this process, we want to say, what are the forces acting on the book? So remember we draw a boundary around the book, and we say, what's touching the book? And so we can see here the table is touching the book. And if we want to think about the long range interaction or long range force, is interacting with the book gravitationally, right? So the Earth would be acting gravitationally. So if we think about our interaction diagram, right, we can say, okay, we've got this book, and we have it in this blue circle. So our boundary is the outside of that ellipse, and we're going to draw then the Earth, because the Earth is interacting with the book because of gravity. That's our long range interaction, and the table is interacting with the book, and that is our contact interaction. The other thing to notice here is that one interaction produces two forces. And so what do we mean by that? Well, the earth interacting with the book, that's an interaction. So the earth is interacting with the book, but the book is also interacting with the earth. So we have two forces, the force of the earth acting on the book and the force of the book acting on the earth. And when we have this interaction, and we always have these two forces that are produced from every interaction, that's called Newton's third law. And we'll talk about that a little bit more later. So step 3. So after we think about our interaction diagram and create our boundary and determine the long range and the contact forces, we want to show all our forces in a free body diagram. And so what we do is we look at our object, we isolate the forces acting on the object. And so for our example, we have the force of the table on the book, and we have the force of the earth on the book. So those are the two forces that are interacting with the book, right? And we identified them through our interaction diagram, right? Our table on the book is our contact force, and earth on the book is our gravitational force. And then what we do is we create a free body diagram. And a free body diagram, what we do is we represent the book as a dot. And so you can see that pretty fat dot there on the page, and right here. And so that dot, what we do is we think about that dot as the center of mass of our object. And then we draw the force of the table on the book. So if I think about the table is pressing up on the book. And so we have the tip of the force from the table right here in the center of the dot pointing upward. And then we have the earth is acting on the book downward. And so we put the tip of the tail of that force at the center of the dot, and we point downward for the force of the earth on the book. And so we're using agent object notation. And so if we want to say the force of the table on the book, we say F, the force, table on book. So agent on object. If we were going to talk about the force of the book on the table, then we would say F of B, the book on the table. The book would be the agent and the table would be the object. And for the force of the earth on the book, we have the force of the earth, the agent on the book, the object. So next we can talk about balanced and unbalanced forces. So when we have balanced forces, what we mean is that our net force in the given direction is 0. So one thing we have to remember is to separate our forces in the X and Y direction. Just like we did for projectile motion, we had to separate the kinematics in the X and Y direction. We have to do the same thing with forces because they're vectors. So in this example, for these balanced forces, we're talking about the forces in the Y direction. So we have the force in the Y direction up and the force in the Y direction down. And so these would be balanced because the length of the arrows are equal. So when they're balanced like this, we have a net force equal to 0. Notice here also that there's no since there's net force is 0, there's no acceleration. If we had a net force say up, then we would have this arrow would be bigger than this arrow and we would have an acceleration up. But we don't. So we now know no net force, so no acceleration. So our object is either at rest or it's moving at a constant speed. When we have an unbalanced force, in this example, our Y forces are balanced, just like up here. But now we have this additional force to the right, and we do not have a force to the left. So these forces are unbalanced. We have a net force to the right in the X direction. And so we know then the sum of the forces are not equal to 0. So our net force is not equal to 0. And that means that we have an acceleration to the right. The acceleration is in the same direction as the net force. And let's see what's next. Next, we'll talk about Newton's first law, or the law of inertia. And so we can define this in a number of ways. And so we have 3 examples here, or 2 examples. So one definition is that objects in motion stay in motion and objects at rest stay at rest unless acted on by an unbalanced force. Or we can say every object continues in its state of rest or of uniform velocity in a straight line as long as no net force acts on it. And one thing to remember is that Newton's first law holds only in inertial reference frames. So this excludes rotating and accelerating frames. Newton's second law. So when more than one force is acting on an object, the object accelerates in the direction of the net force vector. So we talked about that in the last slide, or last 2 slides ago, right? If we have the net force is equal to 0, then our object either remains at rest or remains moving at a constant velocity. But if we have a net force, then what we've done, a net force just means we added up all the forces and they're non-zero. So we have a force that's unbalanced. And so if that's the case, then we have an acceleration, and we can find that acceleration by taking the net force and dividing it by the mass. And our acceleration will be in the same direction as that net force. If we think about this example here, we've got two ropes exert tension forces on a box, and the net force is the vector sum of T1 and T2. And here we can see that we have, if we think about the bottom rope here, right, this force, we're pulling down on the box. So our box is our object, and we have a rope, and we're pulling down on this rope. So there's a force downward. And then there's also a force, we're pulling on this rope up and to the right. And so if we were to pull on this box, we could look at these two vectors. T1 is down and T2 is to the right. And so what we can do is we can find that net force, right? By we can add vectors. So we could say T1 and then we can add T2, and we will end up with this force net down and to the right. And that means that we will have an acceleration down and to the right. We can talk about Newton's third law of motion. And so we talked about that a little bit when we talked about interaction diagrams. And we also have a nice picture here that, that illustrates it quite well. But whenever we have one object and it exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. And we could also say that for every action, there is an equal and opposite reaction. And so to illustrate that here, we have our hand, and our hand is exerting a force on the desk, right? So we're pushing our hand down on the desk. And so that force of the hand on the desk is down and to the right, that pink arrow. But when we push on that desk with our hand, the desk is also exerting a force on our hand. And so that force is up and to the left. So the hand on the desk is down and to the right, and the force of the desk on the hand is up and to the left. So they're equal and opposite. So the one way to think about, well, many ways to think about third law of forces, but good thing to remember is that the forces are exerted on different objects. And so a key to the correct application of the third law is that the forces are exerted on different objects, and make sure you don't use them as if they were acting on the same object. So here's an example where this girl is ice skating, and she goes up to the wall and she pushes off the wall. And so she's exerting a force on the wall, but the wall is also exerting a force on her. So you can see third law pairs, they aren't exerted on the same object. There are two different objects. So the wall on the girl and the girl on the wall, right? So that's how you can tell the difference between, say, third law pairs and second law pairs.